بسم الله الرحمن الرحيم ولا حول ولا قوة إلا بالله العلي العظيم. The last control method that we are proposing for serial manipulators are based on adaptive control, and this is a model reference-based adaptive control that we have in the literature, in the adaptive books. So there are many different methods in adaptation, but before going through the detail of what we are doing, I would like to give a comparison between the adaptive scheme and the robust scheme. In the robust scheme, we talked last session, we said that, okay, we know the nominal model, and we know how much this nominal model is correct, like the boxer, which has a weight of 80 kilograms, and his competitor is, 120 kilogram weight. So he knows that he has 80 kilograms plus minus 40 kilograms, 50%, error or difference in that. And in robust schemes, we work for the worst case problem. We say that, okay, keep your fees as high as much for 50% error in the model, and then hit the system with a bang controller, with a sine controller, or with the V divided by norm of V, as we discussed before, assign and hit the system with a very high gain controller effort. And this make the possible, of course, we have conservatism. We are never, at the top edge of the uncertainty of the model, but we work with the uncertainty to make sure that the system is stable and it is working well. And this means that we require a lot of control effort within the system to add the robustness to the system. And this is usually the practical limitation. Our motors, are limited in the current that we can give to them. Also, we cannot handle very large uncertainty. We can have up to the power that we have only maybe 10%, 20% uncertainty bound on the system. In adaptive version or in adaptive scheme, we don't do that at all. We don't consider that at all. We don't see the worst case, but we look at the system and smartly, it is not like a boxer. It is like a painter. It is something more artistic rather than more powerful. What it does generally in adaptive control said, okay, use the nominal model that you have and check the output. Use the nominal model, consider that it is true. If it was totally true, so you should have a steady state error equal to 0. But if you don't have the steady state error equal to 0, it means that your gravity term is not correct. See how much error you have in the real-time implementation, and adapt your gravity term. For example, you know that there is some problem in the DC gain of the system or in the steady state error of the system. This is related to the gravity vector. Look how much it is, and get a feedback to adapt the system. What will be the problem here? It seems to be very nice. Look and correct yourself. Look the result and correct yourself. And this is always used in many other, artificial intelligence method, in many RL, reinforcement learning, in many other things that you are using. It's like the same thing, it is somehow supervised or unsupervised learning from the outcome of the system. Try something. What you try? The nominal model, the IDC that you have. But correct yourself, adapt yourself. The issue that is important here, there are two issues. First, when you are providing adaptation, so you are changing the system, you are changing the dynamic system. And since this is in the loop, in the feedback loop, this adaptation may diverge. We go to the infinity, and this is problematic. So you should take care of the divergence. You should have always convergence. And the second thing is you are having a non-autonomous system, we call it in nonlinear literature, nonlinear control literature. Now your system is not it's not time invariant. It is time varying because you are intentionally changing the parameters of the system within the time regarding the aspect that you get from the output. So you should take care of the stability of the system. You should make sure that the system is stable. And this is done very, very delicately by Lyapunov analysis, the thing that we have for the system. And this is very interesting that although we are talking about adaptive control, but the basis is nonlinear control since we are using such a thing. Now, let me give the details. You know, I talked about the overall picture here, but the details are quite simple, and you can see that, like before, we consider that we have M and M hat, and these are different. We have B and B hat, C and G. The tilde command or the tilde notation to represent the error, the nominal value from the true value, error in the nonlinear case, and also in the position and the velocity, we consider the true position minus the desired value minus error as a Q tilde in this case. So in adaptive control, as I mentioned, we use IDC. Nothing is changed. Everything is as before, exactly the same inverse dynamic control that we have before. Nothing, we don't add any term to them. We started with the nominal values, and then we try to adapt them. Look how we are adapting that. Here we have a properties in dynamical system that we show that we can represent dynamical system of serial robotic and also in parallel robotic cases as a linear regression. We can have a linear regression based case. We have a matrix plus a parameters, and this is the key point. If we can do that, if we can use that, so the regression will help us to use the least square method or some adaptation law, which I will describe here, to adapt the parameters. So if we say that we adapt the G term or we adapt the M term, we represent that as a parametric form, and we change that parameters. And these are very suitable for parametric uncertainty because it is naturally related to each other. Now, let's do the dynamics. We have the same dynamic, but we know that there are differences between mass metrics. We don't neglect that the discrepancies or the uncertainties here. So here is the dynamic equation of the model of the system, the true system, the robot. M, B, C, G are the true values. It was equal to tau plus tau D. Tau we put it here. From here we have this part plus this part. Now there is a minor simplification. You just add my M E Q Q dot Q double dot to the left, add and subtract to this case, and then you can reach to this point. Let me just show you how you can do that. You do that by yourself, but for example, you see here, we have here MEQ. You can start from here, from the second equation, go back to the first equation. This is much easier to understand, but usually this is done from top to bottom. You see here, MEQ Q double dot, you have something like this. You add a term here. Let's talk about something else. Let's say, for example, this term, BE or CQ dot term. You can see that here you have CQ dot, here you have C hat Q dot, okay? CQ dot, C hat Q dot. and you know that C hat minus C is equal to C tilde. You bring these two together and put it as C tilde. C tilde is this one minus this one. So we have brought everything to the right hand side, all this term to the right hand side, and written the right hand side here. As you see, the tau d comes in here. And you can do the same thing to all the terms. You see that we have we brought this part to the left hand side. You see the minus sign here. You brought it to the left hand side. So you just write this down. You add and subtract this together, and you do term by term. You know, compare them, and you come to this formulation that you come up to here. Why we are bringing this into such a system? Because now we have a formulation very similar to what we have in the dynamic equation, mq double dot plus bq dot plus gq plus tau d. We neglect about the tau d for in the next slide, but this is exactly the dynamic equation that we had before, but it is in the tilde version. It is the error of dynamic, not the true dynamic. And this is very, very important. So we have the structure that we have in the dynamic equation, but we provide that in the error form to use that in the state. And here we have a very simple second order question as we had before. And if there were no uncertainty in the system, this would be equal to 0, and we have the simple IDC as we had before. But we don't neglect that. And we consider that with a linear regression. Now, if you get from here to here, that needs some manipulation, simplification. You can do it very easily by hand. Please do that. You got here now. I just use the m hat inverse to this problem, and just for a moment, just consider that tau d is equal to 0. We put it here. We have m hat here, and we neglect about in the absence of tau d, we have something like this, which we know that this dynamic equation could be written into a regression form, like a matrix times some parameters. And these parameters are the mass of the links, the center of mass, the moment of inertia, a number of parameters that are within the system. And we talk about that in the identification process, how we can find that and how we can do that quite extensively. So we have a linear regression and m hat, and we know that me, and since it is the hatted version, the nominal value, we know exactly m, and we know that m is positive definite, it is always invertible, and we have a linear regression term in here. So we have a second order dynamic equation in the terms of error. Of course, you can, instead of using EQ and EQ dot, I use that to compare that, but you can use Q tilde dot and Q tilde Q dot, and if you do that, this would be positive Q, because E, as you see here, EQ is minus Q tilde dot. You have a dynamic error in a nonlinear format in a Q tilde dot, Q desired minus the error desired double dot minus this is equal to a linear regression. And notice that this error comes from adding and subtracting this term to your system. Now, if you do that and you have this linear regression, you can now use this linear parameter exactly the same way that you did in the robust case. We use a state space formulation for the system. We have a linear part of the system as before, exactly the same thing for the linear part, but a nonlinear part that is here. Over there we have, if you remember, P transpose something, you know, which we call it V in the robust case. Here we have another term. We have B, you know, script Y or gamma phi, that the phi tilde here, as you see, phi tilde is the error of the parameters, not the parameter itself. The error of the why the error of the parameter is because we are using the error dynamics here, not the true dynamics, the error dynamics. And we can get rid of this part by adaptation law. So to make sure that we have convergence and we have stability, first we make sure that the linear part is stable. Exactly the same way, this matrix should be Hurwitz, so we should have positive gains here to have a Hurwitz matrix or a stable matrix here. And this can be considered with a Lyapunov matrix equation for the matrix A. For any Q, you can find the Lyapunov matrix parameter or Lyapunov function. We call it P. ATP plus PA is equal to minus Q. In the MATLAB, you can use Lyap function to find this. Given Q and A, you can easily find P from this method. And then you should take care of this part. This part is still nonlinear, as I mentioned, could be diverging, it should be unstable, and we should take care of that by Lyapunov stability. So we design a Lyapunov candidate, a Lyapunov function candidate. Before we have only the quadratic form for the error, but since we have also an adaptation here, we use a quadratic form on the adaptation law, on the parameters that are varying. And this is very, very general in adaptive case. So the Lyapunov function is consistent, the Lyapunov candidate, let's say, is consistent of two parts. One part is based on the state, a quadratic error of the state with the P, the same P that we used and we found from the previous case to make sure that this part becomes stable using that. And we have another quadratic term with a positive definite matrix. We call it gamma, usually gamma, usually large gain that we can use for the adaptation law. And we would like to make sure that this is, the derivative of this is negative definite for the stability reason. And here the interesting part comes into the picture. If you get the derivative part, the first part derivative gives you something like before, like what we have in robust, ATP base of ATP plus PA, which we call it minus Q. This part is negative since we have stabilized the linear part of the system. And the derivative of that will cause basically two terms. We have, as we call it before, since we have B gamma E phi dot, in these terms, E dot will bring this term into the picture, and the derivative of that will bring this part into the picture. This comes from epsilon dot, this part. From epsilon dot, this term comes into the picture, and this term comes from the phi dot. That you see, we have two cases because this is symmetric, so we have both derivative coming into the picture here. And this could be, this is negative definite, but this could be quite positive. And if this is positive, it means that we are in the instability and we have difficulty for diverging the parameters. But hopefully this is two terms. And we can just, factorize phi transpose here and give the rest in here. The one part depends on the error, and one part depends on the adaptation of phi, how we are adapting it. If we are not correctly adapting the parameters, if we are wildly adapting the parameter, this term could diverge and we are in trouble. But since these two are equal to each other, so we use a very, very nice method. We can make this equal to 0 and find an adaptation law So how to change the phi? This is the decreasing descent, the approach that we use to adapt the parameter to make sure that the stability is conserved and we are converging. If we make this equal to 0, so v dot would be equal to minus e dot epsilon dot q epsilon, which is negative definite and it is stable, but you know, it gives you a very important thing that this shows you how you should adapt. We call this adaptation law. So this is a dynamic equation. Says that when you have phi at the beginning, at the initial state that you have the nominal value, how you should change that. And you see that the change of variables, the parameters, is directly related to the error that you get it at the output. So if the error is large, the adaptation should be large. If error is small, the adaptation should be small. And it is not only this, it has also the positive definiteness or the stability of the linear term here. And we have also a gain, gamma inverse, which is a design parameter. We have another gain, like PD gain that we have another gain here. This is the adaptation gain, and we usually use that to make that adaptation law to be quite, not very fast to make it, you know, oscillating, and not very slow to have a better idea in this case. So this means that, by this means, we make sure that the adaptation is converging, and also the stability of the closed loop system for this non-autonomous case is equal to 0. Is also, the stability is conserved, and this is negative definite. By this means you got to adaptation or adaptive scheme that you start with the system. And what would be the result? You know, since you have started with the nominal value of the parameters, at the beginning you have some problems. You have maybe some overshoot, some errors. But when time evolves, the parameters are adjusting themselves. The parameters are adjusting themselves to make sure that the error becomes 0. You know, you make that the trajectory that the reference trajectory that you are considering is really traversed or really tracked. And this is usually done by this parameter, by this acquiring this adaptation law in the case. And this means that after a while, you know, the system understands what is wrong with itself. If it is a steady state error, as I mentioned before, says that okay, this is because of the gravity terms. That the gravity terms are not written here as gravity at the G terms, they are really written as the phi term, as the parameters of the system that is within the parameters of the system. If we have some problem in the dynamic term, maybe the Christoffel term or the main mass matrix is problematic. And these are all depending on the parameters of the system. The parameters of the system are converging to the value, not the true value. They're converging to a value which is reducing the error of the system. And this is usually the case. If you have the adaptation law, usually you should also plot the adaptation parameters, how the parameters are adapting until the time that they are oscillating. It means that the system has not found its final values. But if they converge to some parameter, some fixed parameter, it seems that now the system has understood the amount of variation that should be given to the parameters. But these final parameters might not be the true parameters, because we never, in the stability proof, we never considered that the phi dot is equal to 0. Here you can see here, v dot is negative semi-definite, basically. If we technically speaking, phi is not in here, it means that phi might not go to the true value of phi dot, or the error of phi tilde might be not equal to 0, but phi dot is somehow that epsilon, the error of the tracking gets to 0. And this is the general behavior that we see in an adaptive controller. We adapt to some parameters. These parameters might not be the true parameters, but they make the tracking error equal to 0. And if we have a disturbance as well here, the disturbance is usually there. We just neglect it, but it is there. This means that the disturbance is there. The disturbance will cause the error to change, and this error will cause the parameters to vary. Again, with, of course, constant disturbance, not varying disturbance. If we have something with slow disturbance dynamic, again, we can reject that through this adaptation law and through this case that we can see. Since this is based on a Lyapunov scheme, adaptation is quite confident. Of course, in practice, there are many issues here which make the design of adaptive control much harder than the robust control. In the robust control, we are quite, we are quite confident that if we have the power, we just use the right and left fist to make the system slow down to the bottom line that we would like. But here they are quite smart, going up and down, but sometimes it is not really in practice. You see that the convergence is not good, or you will converge to some parameters, for example, some negative mass parameter. That is really something is wrong with the modeling of the system. You see a lot of difficulties in practice in implementing adaptation law compared to the robust control. But of course, if you do it correctly, if you have experience in that, that you will find experience in that, you can find finally the case that you need in here. Okay, let me conclude the talk with the last part that we have in here. This shows the structure of adaptive control, and I would like to talk maybe a few minutes, we don't have that much time left, about that. The adaptation, we have the same, if you don't look at that, we have exactly the same IDC control that we had before. We have QQ dot here, we have M hat here, everything AQ here. The only thing is that this M hat, B hat, and C hat, and G hat, which are parameter dependent, are varying or adapting by an adaptation law. And what is required in this adaptation law, this is somehow important. What we require, as you see here, we need to have this one as adaptation law. And as you see, we need to have M hat, B hat, C hat, G hat written in a regression form, which are depending on Q, Q dot, and Q double dot. And also we have the error at the other side. So if you look at that, we need to have Q, Q dot, Q double dot to have the regression form being run, and also the error in the position and the velocity that we can. All of these are good except the Q double dot. Q double dot is very difficult to measure, and we never measure them. And it is not very easy to calculate or to estimate. You need a double filter. We talk about the double filtering and double integration and filtering. This is not good. Of course, in practice, what we do, usually instead of using Q double dot, we might use only Q double dot desired. Of course, this is a problem, it's a difference, but it is much better to have a very smooth Q double dot, as we have talked today. Muhammad told us about the first question in this session, that if we have a step input, we never use a step input in a robotic case. We use very smooth function to have very smooth acceleration here. So this Q double dot is the problem. We don't use that, or if we would like to make it correction, very nice correction about that, we should go a step further in the theory, which we call the passivity-based method. This is a simple correction we do on the system. You can look at the Spong book about the details, and also many other references that take care of that. In that case, we don't use Q double dot, and also we don't use Q double dot desired. Instead of that, we use the dynamic formulation for that, and also make sure that the adaptation law is stable. Not using Lyapunov stability, using something very similar to Lyapunov, which we call in linear control, we call passivity-based method. And this is quite advanced, and I suggest the people who are working in this area also look into this picture. But in any ways, you see that we have the same thing, old thing, just the parameters are changing through a simple, very simple, adaptation law, first order adaptation law, that makes sure that the system is stable. So this is the last thing I would like to say. The only thing which is complementary and very important here, you have to do some simulation. You have to implement that, at least in the simulation. And hopefully in the future you implement these methods in practice for the robot that you will be manufacturing and implementing in the lab or in the industry. Thank you very much. This is all I would like to say. Thank you for keeping with me, coming with me up to the end of the class sessions. This is our last session. I think that we would have some TA, especially TA cases for continuing the problem. We talked about reducing the number of project and assignment in a way that you can reach to the final point that we say that we would have only 2 assignment and project being left, one from dynamic and one in the control part, that you use the simulation and everything to reach to the final point. And we would have our final exam exactly on the time that it is assigned on your exam book, exam sheet, in exam schedule, which we will follow that quite accurately. If there is any question, please let me know. I just want to bring the... هم سوال کنم علی آقا در خصوص اون برنامه که با هم صحبت کردیم توضیح بده، بچه‌ها تو جریان باشن.
من در مورد همین کنترل کننده سوال داشتم، خیلی سریع هم سوالامو جمع می‌کنم که بقیه بچه‌ها اگه حرفی دارن بزنن. میشه اسلاید رو ببخشید خیلی. اسلاید 52. من حقیقتش اول یه هیستوری میگم که بگم سوالم چیه و شاید جالب باشه. من حقیقتش اولین کنترل کننده که یه بار وسط واقعی روی ربات مثلا همین کنترل کننده ادپتیو IDC بود. در واقع از بعد تقریبا سخت‌ترین شروع کردیم. بعد خب همونطور که می‌دونید این کنترل کننده مال جناب کریگه، مال الان که من نگاه کردم مال 1985 ایکرا 1985 بعد 1986 شده تو IJRR. بعد خب کنترل کننده خیلی خوبیه. ما موقعی که اولین پیاده سازی کردیم رو ربات دیدیم ربات ناپایدار میشه، یعنی در لولی ربات ناپایدار شد که
تقریبا شک
دقیقاً من تو کل عمرم 2 بار کابلای ربات دایموندو پاره کردیم. یه بارش دقیقاً سر همین کنترلر بود. بعد حالا ما موقعی که داشتیم اینو با تو پرانتز عباس داشتیم میبستیم، تو 2 تا موضوع شک داشتیم. در واقع
خاطرات میگیم.
آره عباس میگفت این انتگرال گیر مشکل داره، من میگفتم شتاب اون اندازه گیری شتاب مشکل داره. بعد جفتم اوکی کردیم. بعد متاسفانه شبیه سازی هم نمی‌کردیم، کلا به شبیه سازی اعتقاد نداشتیم، کلا یه راست پیاده سازی می‌کردیم. بعد دیدیم هیچ کدومش نشد. بعد آخر به نتیجه رسیدیم یه چیزی پشت این قضیه وجود داره که ما نمی‌دونیم. بعد همه اینا رو گفتم که این سوالو بپرسم. حالا من خوندم اینا رو تقریبا میدونم ولی قانع نشدم که الان توی این قانون تطبیق تو این فیتیل دات یک گاما ترانسپوز وجود داره، تو اون گاما یه ماتریس چرنی وجود داره که تو اون ماتریس چرنی اینورس شده. من از نظر کنترل غیر خطی هیچ وقت نتونستم بفهمم که چرا این ماتریس چرنی اینورسش باید باندد باشه. این سواله
خیلی سوال خوبیه ولی خیلی ادوانسه به خاطر اینکه پرکتیکاله.
بله تو پرانتز بعضیا نوشتن مشکل رو ندیدن، بعضیا ما مشکل به چش دیدیم. نمیدونم چرا.
معمولا یعنی اگه کسی ندیده شانس نداره. در واقع این نکته که من میگم بچه‌ها این تجربه منه. هر دفعه بار اولی کار رو انجام دادید خوب انجام شده، راحت انجام شد، خیلی بد شانسه. فکر نکنید خیلی خوش شانسه، چون خیلی چیزا رو یاد نمیگیرید. و من جز خوش شانسام، یعنی هر وقت هر چیزی رو بستم اول ترکیده، بعد کم 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 حاضر. خیلی سوال خوبیه. ببینید در واقع اینجا همونجوری که ملاحظه میکنید هم ما یه مدل دینامیکی داریم، هم یه اینورس ام اینورس داریم. آیا مدل اممون آیا به اصطلاح پایدار هست یا نه؟ خوشبختانه من اینو دارم. شما اگر تو پراپرتیز اکچویتر پراپرتیز بریم، اینا حالا چرا مهمه؟ من یادم نمیاد فرمولیشن. بله اینجا نگاه کنید، میبینی علی جان؟ نمیدونم حالا با تأخیر اومد یا نه. هم ام باوندده هم ام اینورس باوندده، هم ام باوندده. این اسلاید 38 اولین پراپرتی که ما داریم میگیم برای ماس ماتریکس. میگیم ماس ماتریکس یه پوزیتیو دفینیته به خاطر این باوندد upper and lower bounded. upper and lower bounded وقتی upper and lower bounded چون ماتریس M یه ماتریس پوزیتیو دفینیته، ماکسیموم هم آیگن ولیوهایی که خواهد داشت یه مقدار خواهد بود، مینیمومش هم یه مقدار خواهد. ماکسیموم برای upper bound M مد نظر قرار میگیره، مینیموم میبینی اینجا لاندا مین برای ماکسیموم باوند بودن M اینورس در واقع در نظر میگیره. بنابراین واقعا اینجوری هست، یعنی ام اینورس ما مشکلی نداره به لحاظ تئوریک. ولی چه اتفاقی میفته؟ نمیدونم جواب تو گرفتی علی جان؟ این اسلاید 38 درس و همه جا هم هست.
38 من قبول دارم، هم صدا من کم دارید. من سیاسی کاملا قبول دارم. ماتریس خط هم باندده. ما حتی موقعی که ربات رو شناسایی کردیم حتی پلات اینم کشیدیم که بگیم آقا این یه باندده، یه نموداریه، یه خط بالا داره، یه خط پایین داره. ولی بازم موقعی که ما کنترل کننده رو می‌بستیم ناپایدار.
خب آفرین، این یه چیز دیگه است. این که از کجا میاد؟ خیلی سخته من اینو بخوام بگم، چون حقیقتش خود منم خیلی تجربه تو ادپتیو ندارم. یعنی خب البته آقای دکتر صدیق که خب ادپتیو کار ماست، همیشه توی پایان نامه‌ای که داریم میگه که من خیلی خوشحالم چون ما همه این کارا رو تئوری انجام میدیم، شما عملی انجام میدید، شما بگید که چی میبینید. معلومه که در واقع یه فاصله بین تئوری و عملی وجود داره. یعنی این بحث ادپتیشن و ترکیدن ادپتیو، میدونید باز تاریخی اگه بخوایم بگیم، ادپتیو بعد از اینکه ما اون اوج نایکویست و اینا رو تو سال 45 داشتیم، حدود سال 60 دهه 60 ادپتیو اومد و وارد شد و اولین ادپتیشن اولین کنترل ادپتیوی که پیاده سازی شد ترکید. همین کاری که تو میگی و این باعث شد 20 سال ادپتیو عقب بمونه. حالا علت چیه؟ علت واقعیتش اینه که خیلی من خلاصه بخوام بگم، ما اینجا داریم فرض میکنیم که پارامتریک آنسرتینتی داریم. خیلی روشنه، ولی سیستم واقعی فقط پارامتریک آنسرتینتی نداره، یه چیزای دیگه هم داره، مثل استکاکایی که داشتی و ندیدی، به خصوص تو کابل. اونو کجا میاریم تو این؟ ما داریم فورس میکنیم تو این پارامترها واردش کنیم. ببین من اینجا گفتم همینجا گفتم تاودی اگر وجود داشته باشه، ما اینجا تاودی ندیدیم، اگه وجود داشته باشه، اگه تاودی شبیه گراویتی ترممون باشه، ترمای گراویتی تو تغییر میده، اوکیه. اما فرض کن یه تاودی داری که در واقع مثل استکاک بالا پایین داره میشه، و وقت اینجا این اصلا یه فرم اسموت نداره. ما موقعی این کاملا درسته ها، این چیزی که اینجا میگیم تئوری کاملا درسته، فاصلش با تئوری و عمله. باز دوباره برمیگردم رو اسلاید اول، رو این اسلاید کجا بود؟ روباست اند ادپتیو، اینجا اسلاید 43. شما اینجا میبینید که structured uncertainty اگه داشته باشیم اون وقت ادپتیو خوبه. unstructured داشتیم چی؟ ادپتیو نمیتونه برای unstructured کار کنه. یعنی یه ترمی تو مدلتون هست، همون جوری که شما خوب علی به خوبی دیدی تو آیدنتیفیکیشن که انجام میدی، یه ترمای هست آیدنتیفای نمیشه، بقیه هم خراب میکنه، نمیکنه؟ این اونه مسئلهش. و اون چی جوریه؟ برای چی من اول روباستو گفتم بعد ادپتیو گفتم؟ نه برای اینکه من روباست کارم مثلا کتاب روباست دارم، نه، پرکتیکالی ادپتیو اصلا فرضمون اینه که یه لیست اسکوئری داریم و این در واقع داره با این لیست اسکوئر داره کار میکنه. ما داریم در واقع یه لینیر ریگرشن داریم حالا لینیر ریگرشن اگه به هم خورد فضا کلا میترکه. یعنی این که یعنی چی؟ یعنی این اثبات پایداری یه فرضی توش وجود داره، اون فرضش از بین میره. وقتی اون فرض از بین رفت کار خراب میشه. و البته من دوست نداشتم اینو امروز بگم، چون من تازه اینو معرفی کردم بچه‌ها، نمیخوام پنبهشو بزنم زیر آبشو بزنم. توجه کنید هر کدوم از اینا جای خودشون قرار میگیره. بنابراین اصلا مشکل از ماس متریکست نیست، از آن باوندد بودن ماس متریکست نیست، از این گاماه نیست. به نظر من موضوع از یه چیزای دیگه است که تو مدلت نگاه نکردی و اون داره اینا رو تحریک میکنه. حالا یه موقعی شانس میاری، اونا کوچیکه، تأثیر زیادی نداره، شانس نمیاری، نمیبینی این مسئله، کابلت پاره نمیشه. یه موقعی همچین اتفاق میفته، کابل پاره میشه. چرا؟ چون شما دارید تو حلقه این کار رو میکنید و این کار بسیار سخت. من به هیچ عنوان توصیه نمی کنم که ادپتیو و مستقیم روی سیستم واقعی پیاده کنید. حتما سیمولیتش کنید، حتما ولیدیتش کنید و بعد این کار رو انجام